is it off? Oh, sorry. Yeah, got it. We'll be presenting on getting started with Rholang contracts in less than 30 minutes. So first, we'll be walking through how to get the Rholang node up and running. And then we'll go through some basic Rholang productions. And then Mike Stay will run through how, or basically run through the examples of the Rholang Mercury tutorial. And so one thing we noted is that if everyone went along with this process and installed VirtualBox in Ubuntu right now, it would probably crash the streaming. So maybe I'll just run through, just show you that this process should be really straightforward. If you have a Mac, you're in luck because you can just download Docker Mac and use that. Otherwise, you'll have to go through the process of installing VirtualBox and then getting Ubuntu 16.04 running on that. And then finally installing Docker. But hopefully that is pretty much a straightforward Docker install. And then after that, all you really have to do is run this one command. And if you don't already have the Archain Docker node downloaded, it will pull it in for you and run the REPL. So yeah, that is actually it in terms of installing the REPL. If you try this out later and you have trouble, sure. Yeah, these are all on the Archain website, and they should also be in the GitHub README. But yeah, if you have trouble, basically talk to any dev here. There shouldn't be any surprises here. But yeah, once you get this running, just type in a contract and basically you're good to go. So the only warning about the REPL is that you can't paste in new lines as of now. We'll try to get this quickly up, but yeah, you'll have to remove all the new lines before you paste in anything. But yeah, that's sort of it for the getting the node up. So now just onto Rholang productions. And so what I find useful when mentally executing through Rholang code is to have this idea of a table. We call it the tuple space, but really, if you just think of it in your head as a table where this table maps channels to the code or data that is stored at that channel. It's really useful. And with that in mind, when we go, let's go into the input statement. So we have, for the input statement, the syntax is for, and then that's a keyword, and then the pattern, which is from a channel, and then the continuation. So if we look at this in sort of Python pseudocode, it is effectively the same as getting the whatever code or data was at the channel in the table I previously mentioned, and then seeing if the pattern matches that channel. And then if it does, it executes it. And so this is a bit oversimplified. And so if we expand it a bit more, first of all, the equality is not an equality. It is a match statement that Kyle described earlier if you were at his presentation. But for the simple cases, it does sort of reduce down to equality of the pattern and the target, or the value that was returned from getting the channel. But the other aspect of this is that if the pattern does not match the target, then we need to put back that data into the table, or technically the tuple space. And then we would technically loop back to the top in the sense that, we're always trying to listen for more things from the channel. And so that is the input. And so now we go on to contract. So contract, if you notice, is actually not really different from the input. And in fact, if we ignore the blockchain semantics of the contract, it's basically the same, except, well, it is persisted. Or to be concrete about that, when it matches something and then it creates an actual copy, it's sort of waiting there again to receive more inputs at that same name. And so I'm sort of translating that into Python pseudocode here. I just said, if it matches, we loop back to the top and we try to continue to listen for new things coming on the contract name. Yep. And then, so then we have sends, which I've sort of called bangs or produce. Basically, here we just send data on a channel. And so this is, the simple way of looking at it is you just put the data at that channel. And, there's all sorts of other things the tuple space does. But at its core, this is what it is. And so then next we have the new production. And so this just creates a new bound variable with some kind of private, effectively we use a UUID. But yeah, the idea is we just now have this new name that we can use within the scope that is private. So then finally we have par, which, as you can probably see, it's probably easier to explain in Rholang, which is that, you just run P and Q at the same time. And yeah, that concludes most of the productions that might be unfamiliar. We, of course, as Kyle was mentioning earlier, we have our expressions, we have the match, but those, or at least in my opinion, they transfer more or less well from other languages. And so just what I wanted to go over here is just how you can convert from processes to names and then vice versa. And so to go from a name to a process, you just star that name and then you get a process. That basically, that star you should think of as evaluate. And for going from processes to names, you quote the process, and that sort of freezes that from running, and you can use it as a name. And so just to make sure, this is somewhat review if you were in Kyle's presentation earlier, but here are the various places where you would expect a name context versus a process. And so yeah, you would you want to listen on a name for a name, and then the continuation's a process. For contract, the contract name is, of course, a name context and the arguments for it, and then the continuation of it is a process. And for sending, you send on a channel, so that's a name context, and you send a process through. And so just to be clear here, what I guess I like to think happens internally is that you take this process context and you would implicitly quote it so that when you're sending it through the channel, you're not actually executing it, if that makes sense. So yeah, that's sort of the way I think of why it's a process context. So then for the new, the name that you create there is of course a name context, and then the body is again some process. And then finally, when you run two processes in parallel, they are both process contexts. And so yeah, that is sort of an overview of the productions. Hopefully that was just more like review from what Carl said earlier. But at this point, is there any questions?
What are the semantics? The rest of the world.
Sir, what are the semantics if there's more than one match?
If there's only, when we have a for, you can only, you either match the entire pattern or you don't. And are you referencing to the fact that maybe your pattern might have multiple items? Is that? Okay. So if it has multiple items and it fails to match, even one of them, then it doesn't match.
One match in the R space.
Oh, I see. Then it randomly picks one and it executes that. Yeah, and that's sort of how the non-determinism is created currently. Any other questions? Okay, so if not, we'll have Mike Stay go over the Rholang Mercury tutorial and the examples that come with it.
Okay. Is this working? The Rholang tutorial that I'm looking at here is the one that is on the website. It's on Archain GitHub repo. This was our view of what we wanted Mercury to be like a month or two ago. This language is constantly in flux. We're coming up with new ways to approach things, new ways to structure things. So the syntax that we're going to look at here is not exactly the currently supported syntax. It's not exactly what we're going to support, but it's very close and captures the intent pretty well. So we're starting off here. Let me make this bigger so that it's easier to see. Start off with a contract. And just as an illustration, this is listening on this name here that is the quoted process hello world. This tutorial is aimed at system contract writers rather than blockchain contract writers. So here, this contract is expecting to receive a system object. This system object is the encapsulation of all of the authority to cause side effects outside of a system outside of a system contract. So this thing here is expecting to be invoked or receive messages, and the first argument, it's expecting to be a method name followed by parameters for that method. This one is a fire and forget version in that there's no return channel to listen on in this particular invocation. So it'll say print, but it has no idea when that print has completed. Here's a slightly more complicated hello world. Hello again. It's waiting for the system object, but it's creating a new channel to communicate on. And this idea of creating a new channel is really the thing that separates pi calculus as a process calculus from all of the process calculi that came before it. So when Milner in 1990 invented pi calculus, he had already done a few other process calculi earlier, but those ones had fixed topologies. The earlier ones were for modeling ARPANET as it was set up. They had a fixed number of computers and a fixed set of connections between them, and they were trying to reason about how processes would run on those individual computers and exchange messages. PyCalculus, on the other hand, has this new construction. It says, now that we have TCP/IP and can route any way we want to between two computers, we don't care about the physical connections. We just want to establish a connection with that remote computer and use it. So this is establishing a new channel on which we can send messages. Greg's insight was that in PyCalculus, the set of names is a parameter to the theory. You've got the terms that are built up out of the names and the other productions, but the names themselves were just sort of plugged in, that there was no a priori structure on the names. And in fact, Milner said these names should not have any structure at all. Greg wanted a more self-contained theory, and so he said, clearly we need a countable infinity of names. There's no upper bound on the number of names we might use. So where do we get this countable infinity? We could use natural numbers. That's, you know, a reasonable choice. But he said he wanted to be able to distinguish sets of names from each other. So he took the productions that he had from the calculus itself and then closed the loop, did a recursive fixed point. And so then the processes that we had a countable infinity of became the names. And all you do is stick an @ sign out front of a process and you get a name. That's how this quoting process thing came to be. So right here we're creating a new name. Now, as Kyle said earlier, each new name, anything formed in this way, is the quote of an unforgeable process. Sometimes we'll say private. It's not exactly private because everything you send on the blockchain is visible to people observing the blockchain. But if you're a contract within the blockchain, there's no way for you to send or listen on one of these unless it has explicitly been passed to you as an argument. So in that sense, it's private. So what do? We take this channel and we send on it hello again world. Now, we talk about these things firing. The syntax just says we do both of these at the same time. There's no implicit order. But when we deploy this, we have to convert it from this code that's been deployed into entries in the tuple space. And so this one may go into the tuple space first, or this one might go in first. And there's some non-determinism there. Yes. Just a sec. Let me hand you a mic.
I'm actually trying to compile it right now, but I get a syntax error. And in new, it says new, it doesn't recognize it.
As I said, this syntax is not exactly the syntax that is currently supported. I'm just going over the concepts using this tutorial because it was already written. The problem is that the current syntax says you have to have an open semicolon here. You can't go straight in. I'm sorry, not semicolon, open curly brace right there. You can't go straight into new. I will get to actual running code after I go through the concepts that are explained here in the tutorial. So this one says send it on the channel. This says listen on the channel. Now we have two different orders where those might go into the tuple space. If this goes in first, it's like storing a piece of data in a key-value data store. You just say store this string at that key, right? Then when this one comes along, it says go to this key, and if there's any data there, bind that data to the process we call text, and then use it in the body. Now again, I think the current syntax forces curly braces around the body here, but that's not my main point. It's that there was data there, and then this behaved like a query. You know, it went to fetch the stuff at that key, took the data that was waiting at that key and stuck it in here. Now, as Kent said earlier, you can have more than one value at any key. And if you go in and grab one, it will non-deterministically hand you back one of those. There's a different nonlinear arrow here that will keep pulling until there's nothing left. But now let's consider what happens if we do it in the other order, how it could have happened. The query comes in first. There's no data there yet. So what happens is, at this key, it stores lambda text dot system print text. So it stores a closure that is waiting for data to fire, and then the body of that continuation. So it's waiting there with a query, hoping that data will show up eventually. Then when this gets in there, it finds there's a query waiting already, so it pulls the query out, sticks in this value for text, and executes it. Now, it's a little bit more complicated than that because we support arbitrary kinds of continuation, not just Rholang terms. It might be compiled Rosette code, it might be Scala code, and if you choose to use it yourself in your own projects, it could be Python code or JavaScript or whatever you want. But for the purposes of this, we're going to stick to Rholang continuations. All right. Are there any questions about what we've got so far? Yeah.
Just a quick question about the non-determinism. Yep. So if there's, say, world or you, say, as like examples of text, so it'll pick one non-deterministically, but if that executes on the blockchain, which is the outcome if it's validated on other nodes?
Yeah, that's a good question. That is part of the point of the consensus algorithm, is to decide everybody to come to agreement on which of those non-deterministic possibilities was actually chosen. There's another question over here.
Yeah, just quickly for the consistency of the example, could you quickly tell what text is, because it came out of nowhere, and also the text is as probably a process which is quoted to be a name, but then it's being used without being unquoted, or how that works?
Sure. So in Rholang, like row calculus, you send processes, all ground terms like strings, numbers, lists, sets, maps, etc. Those are all processes. And you receive names. So right here, we expect to get a name out of Chan. Even though we sent the process hello again world, what we're going to bind to what we expect to receive is the quoted form of that. So we get quote, hello again world. What this is a pattern. This says, I'm expecting a name here, and all names start with an @ sign. So I'm going to grab the process that follows the @ sign in the quoted hello world. And so text itself is bound to this string. Then when I use text over here, it is the process, quote, hello world. Or string hello world, yeah.
And why exactly are there actual quotes around hello again?
In order to delimit the string.
The word contract, could you speak a little bit about that?
Yes. Contract is a keyword in the language. It has a meaning very similar to persisted for. So it is waiting for input at a key. So the key in this case is the string hello again. Okay, so that's one of the keys in the tuple space. Contract says store this continuation at the tuple space, but when data comes in, don't get rid of the continuation. It's not a single fire thing, it's a persistent thing. So every time data comes in, it will fire off a new copy of this body with system replacing that value. Now, in the case of a system contract, we expect this only to run once, that we deploy a bunch of system contracts that run at boot up time, and there's only one system object. But in general, we will get contracts, and we'll see that later, where contracts can be invoked multiple times, and they don't go away. Any other questions about this?
So if you needed to version a contract, but you wanted to have a similar name, or I guess how would you handle versioning of a contract where the execution code is different?
So contracts can have state. Part of that state can be code itself. So if you want, you can create a cell contract or have a cell inside your contract that holds the current contract to be executed, and then have a method that only code that you trust or that only you can deploy to will update that code that will be run. On the other hand, if you want to maintain old versions and have them still available, then you can do something like adopt a convention that a particular version is at something like this, where it's a list containing your contract name, whether it's forgeable or unforgeable, followed by a version number. And then people can access it, pick whichever version they want, and send to that name.
So from your last answer, I take it that contract is one of these flavors of consume and produce?
Yes, contract is a consume.
Okay. And is there a complete list of what the keywords are for the various flavors?
Yes, you can find the complete grammar for the language in, well, RChain, etc.
Okay.
Under the Rholang project.
Thank you.
Any other questions about this code? Yeah.
The print is a system object, right? So, because that's also in quotes.
Print is a method name on the system object. So in this case, I'm selecting print from among a whole bunch of possibilities. This is one style of doing object-like method invocation, where you're expecting the code running, listening on this name to expect a method and then doing dispatch internally. We'll see that there's another way of doing it where each method gets its own name that you can invoke. Any other questions? Yeah.
What might happen if you called some sort of string method on system that didn't exist?
The error model is currently under active development. As Kyle said, at the moment, it would crash the interpreter. We have some discussions planned for this week after the developer conference to go through various proposals in other languages that are similar to ours for error models, things that we would like to have happen. Do we need to thread through error channels to return them on? Do we simply write to the ground term, quoted ground terms that are in the bottom namespace and therefore just thrown away, but you can watch for it elsewhere? It's all very undecided at the moment as to what happens when things go wrong.
Are there leading candidates?
Nothing that I can take time now to discuss. It's still very underdetermined. Okay, so this is where we get to the mutable state I mentioned earlier. This is making a cell. This, we can think of make cell as kind of like a constructor. It gets an initial value, and because it's a value, what we expect to be a ground term, we're using an @ sign there to say, I want this to bind to the process part of the name we're using. But then we have two names, get and set. So in this case, rather than having the constructor create these things using new and hand them back to the client supplies these for the constructor to use. First thing it does is create this channel called value store. Now, values, all channels are keys in the tuple space. So what this does is store the initial value at that key. Now, one of the invariants of this code is that there will either be a value stored at that key or no values stored at that key. That gives us lock-like semantics. So the next thing this does is, let's see, how's that go? For each, that shouldn't be doubled. This should be a single one. so it reads the value out of the value store, binds this to the process, and then one of these two gets to execute. So if there's a channel waiting on get, that is, if someone has invoked get. Oh, I'm sorry, I'm wrong. This is correct. This is a replicated for, so it won't be removed. It's very much like contract in that way. But there's only one that'll ever be there. The point of deploying it with this replicated for is so that it never goes away. So this reads the value out, then one of these two fires. If there's a get, then it puts the value back into the data store. So it pulled it out first, then puts it back, and then it also sends it along the acknowledgement channel. So every time that you want to get information back from a process, you have to send along some channel for them to give it to you on. So here it says, I want you to give me the value, send it to me on this channel. For set, you provide a new value, and so it has already consumed the one that's there, it puts the new value back instead, and then it lets you know that it is done with that by sending the empty message back along the ACK channel. So you don't care what you receive in return, but you need to wait to be notified that the set is complete. So that's what this ACK channel is for. Here's an example of the usage. So as a client, I am creating the get and set channels. I provide them with the initial value to make cell. So this creates a running instance of the cell that I can interact with. Then I create a return channel for it to talk back to me on, and I say, get the current value, and send it to me on ACK. Here I am listening for the result. And when I get the value here, it gets bound to result. I send system.print result. Now in this case, print expects either, well, it expects an arbitrary number expects 2 or 3. So the view we saw before did print with a single thing to print. This one has a third parameter that is the return channel to say, okay, I'm done printing. So this says, send this result, 1, 2, 3, to be printed, then let me know when it's done. Here I wait to be notified that it's done. Then I set the value to 4, 5, 6 and say, let me know when it's done. Went on the ACK channel. I wait to be notified that it's done. And then I get the new result. Similarly, come all the way down here and print it out. But at this point, I don't care to be notified anymore. So what we ought to see is 1, 2, 3 gets in there. We print 1, 2, 3 here. We set it to 4, 5, 6. Get it. It's 1, 2, 3, and we print it there. Questions about this piece of code? Yeah.
Is Rholang intended to be a language that humans write or a compiled target?
It is intended to be one that humans write. This here is what they call in JavaScript land callback hell, right? If you want to do things sequentially, you end up having to say so explicitly in the language. For Mercury, we're going to leave it this way. For Venus, we will have a total functional sublanguage where you can string together things explicitly and sequence them. But for now, it's going to look mostly like this. This was something that Greg was pretty insistent on. He wanted to make sure that people bent their minds enough to understand what was going on without falling back to comfortable old patterns. So he wants this for Mercury. He's paying the bills.
So is it? I may be missing something. Or is result a keyword, or is that where was that? Where did that come from? I guess, or how did that get assigned?
Result is used a couple of times. This is a binder. Yeah. So just like if you say function open paren x, x is magicked up out of nowhere. It's a formal variable. Here, it's a binder in much the same way. Yeah. And so then I can use result inside here. There and again here. This one shadows this one. So this result is not the one that was bound there. It's shadowed by this binder. Just in the same way as if you said function X and then inside that you had a local function that also used X, it would shadow it. There was one over here, yeah.
I was going to ask the same thing about the two results and whether one shadows the other. So now my question is, if we hadn't used result again on lines 24 and 25, if we had called it result 2 or something, do we still then have access to that original channel?
Yes, we do. It's lexical scoping. Yeah. Any other questions on this code? So the mutability of the cell relies on the fact that we can pull something out of the database and put something else back in. That's the basic idea. So we've got some key, we're pulling things out, putting them back in, looking at the current value, that sort of stuff. Yeah, just a sec. Cody?
Sorry, this is just a nitpicky question. Is there something in this code that prevents two values from being stored in the same cell?
There's nothing that prevents it, but it is a provable invariant of the code. So let me scroll back up to that part.
No, that's a fine answer. If you wanted to guarantee that you're not shooting yourself in the foot, is there a way to do that?
There will be in Venus. It will be in the behavioral type system.
Okay.
Yeah.
If I have a process listening, waiting to receive several input arguments, and I send single arguments, but from several different processes running in parallel, are they going to satisfy all of the arguments that I'm listening for?
No, each message has an arity, and unless the message arity matches, it doesn't fire. So if this thing here is expecting 3 and you send it 1, it will merely store that message alongside this continuation and they won't synchronize with each other.
So is there any distinction between waiting for several arguments and waiting for a list that contains?
Yeah, if you want to send several arguments, you do it all at once. We will see in a little bit how to receive multiple arguments from multiple clients and wait for all of them to arrive at the same time and then proceed. So that's called a join, and we'll get to that.
Okay, thanks.
Any other questions on the cell? All right. This is a method on lists that is not yet implemented, but the idea is that I create a new channel. I've got this list, and I want to send each of the values in turn on Chan. So here I get the value, and then I also declare an acknowledgement channel and pull them both off using this special operator from Chan. What this says is, after I receive the number, print it, and then signal for it to send the next number. Okay? So I need to get both the number and where to signal it from. Signal it back. This ACK ends up being desugared into something that iterate is listening for. So before iterate starts sending things, it listens for the ACK channel, which is declared here, and that's part of the protocol with that double arrow. This is stuff that's intended for Mercury, may not make it in until Venus. Shows the potential for these different kinds of arrow to express different semantics in the way that they communicate.
These double arrows you showed before, in the iterate example, exactly what do they mean? Because we know, for example, the arrow and the equal sign, which continuously fetches something, but what do they mean actually?
So the continuous fetching is different from the double arrow. There's linear arrow, which means fetch exactly one data and then go away. So you wait. If there's no data there yet, it puts it into the database and waits. As soon as 1 comes in, You may get a deployment with 2, and then it'll pick one of those non-deterministically. But as soon as 1 comes in, it will combine with this and fire the continuation only once. Double arrow with the equals sign is like contract. The difference is that contract says, I will not pay for the processing of messages I receive. It's up to the sender to pay for it. Whereas 4 says, I am willing to pay for messages I receive. The double arrow here means no matter how many times I get data, leave the continuation in the database. And then the double arrow left shift sort of operator that shows up in this proposal is a sequential consume, that you not only have a list of values, but the last one is a channel on which to acknowledge that you have received it. So it's a way of sequentializing a bunch of data that's coming in. If you just deploy a whole bunch of messages at once, it's non-deterministic in which order you get them. But if you use this thing, then you have the ability to say, send him this one, and then this one, and then this one in order. So that's what this proposal was about. Coat check. So the idea of a coat check is you're going to go eat dinner at a nice place, you want to hang up your coat, you hand it to the guy at the front, he puts it in a spot somewhere hanging up, or you hand him your purse, backpack, whatever. They hand you a ticket back, and then you can go back later and claim it by presenting the ticket, and they'll give you the thing that corresponds to it. So this is intended to play that kind of role. Make coat check takes a return channel. Then we get this new IO pair thing. This is a security pattern. So if you have a name, you can listen on that name. If somebody else gave it to you, the name of their contract, you could spawn another contract and start listening and begin intercepting messages that clients may have thought should go to them. So you can intercept messages for someone else. With an IO pair, this one can only be used for input, and this one can only be used for output. So if you hang on to the input one, you're the only one who can receive messages, but you can hand out the output one for all of your clients and guarantee that nobody else can intercept messages intended for you. This table is the set of boxes in which you're going to store the backpacks, more or less. Here on the return channel, I'm going to be using an object-style interface. So I'm going to expect things coming in on port in, and the first part of this is going to be a string picking out the method. So I'm doing an internal dispatch. This ret channel is where I'm going to send back my object reference so that people can invoke it. So right here, I send port out on the return channel, and I begin listening on port in for the method name, where to send the acknowledgement of the result of the method call, and the rest of the parameters. This is not yet supported in our current syntax. Kyle's working on it, probably ought to be in the next week or two. Here is pattern matching. So it's matching the method against some strings. If we're creating a new one, then it looks at the rest of the arguments and says, if it's a list containing the initial value, then we do this. So this is expecting one more parameter. What it does is create a new ticket, send that ticket back along the acknowledgement channel, and then pair it up with this internal table to create a new name that's a compound of both the ticket and this other thing. So if you've got the ticket, I'm not storing this on the ticket itself, but rather I'm storing it on a name derived from the ticket and this other unforgeable name. So you can present it back to me to get the data out, but nobody else with the ticket can do anything with it. It's just a random new unforgeable process that doesn't do anything. It's only when you present it back to me in the get case that you can get your initial value back. So here it says I'm expecting one more argument. This was a proposal that says read and put back, so I don't have to explicitly say put this value back onto this thing once it's been gotten. This is something like a cell so that you can get it multiple times. But here it says, read from the place where I stored the value and send it back along the acknowledgement channel, but also put it back where you got it. Finally, the set function gets the, let's see, what does it do with store? I think this must, I think this is wrong. Let me check. Store isn't ever used in the body, so it must be wrong. Anyway, this must be ticket. That's it. So you present your ticket and the new value. It combines it with the table to find the place where you had stored the old one. So it grabs the old value, but immediately discards it with this wildcard. Then it puts the new value into that spot in the cubbyhole and acknowledges that that has been done. So we can go through usage, but it does what you would expect. The nice thing about the coat check example is that you can go on and use it. Let me scroll down past some of this stuff. Use it for object capabilities. Logging forward or accountability. There we go, sealer-unsealer pair. So this is a version of the coat check example that doesn't have set. Why would that be useful? Well, it plays a role very like signatures. What I can do is put a value into a coat check, give you the ticket, and since I'm the only one that can provide a ticket by which you can get this value out, I must have been the one who put it in there. So it's a way of proving that I had it to begin with and giving you a copy of this thing where you can go to the coat check and validate, yep, he put this in here. This ticket works to get the value out without using cryptography. So earlier Nash was talking about how we can do lots of these design patterns that used to use cryptography, but now we can do them using things like object references that don't actually need crypto. So let's see here. Dining philosophers. Now we get to the join question. So the dining philosophers is a problem in process calculus where you've got lots of processes contending for the same resources. Say we've got a table, and on the north side is a knife, and on the south side is a fork. And sitting on the east and west are two philosophers. These philosophers are picky about the way they eat. They always grab the utensil at their right, and then grab the utensil at their left, cut a piece off their food, put them back down. So right here, we say, get the knife on my right, get the fork on my left, do the thing with the knife and the fork, and then be done. Down here, the other philosopher does the opposite thing. So what's going to happen? Well, these are running at the same time. Philosopher 1 grabs the knife, philosopher 2 grabs the fork, and they starve to death. So this is process starvation. The solution is joins. With the semicolon here, you say, only fire this when there is both a knife on the north and a spoon on the south. When both of them are available and I can get both, then do this thing, but leave them on the table otherwise. That way, anytime, whichever one of these fires first is guaranteed to have both resources it needs, and then it releases them, and then the other one can go. Cody?
Could that be done equivalently with a pattern match?
Well, these are patterns. So in this case, I'm just expecting a name so I don't have to do anything fancy. But if I wanted a resource of a particular form, then I could put the pattern there, and it would only fire when resources of that particular form were available.
So, I mean, instead of using the semicolon
No, the semicolon is the join operator. This is necessary. This says when this is available on north and this is available on south, then fire. So that's how you get multiple things sending in messages and only progressing when all of them have been received.
I see. So conceptually, there could be an extension of the pattern matching that includes joins, but it's not.
Joins are in the interpreter right now. At least I think so. I guess Kyle isn't here to answer, but I'm pretty sure they're in at the moment. Kent, do you know? Yeah, they are. Okay. So joins are available on the interpreter. Let's see. There's an American riddle that says, how do you make 15 cents in change when one coin is not a nickel and the other is not a dime? So nickel's worth 5 cents, a dime is worth 10. Right? How do you make 15 cents when one's not a nickel and the other's not a dime? Here we have replicated send. So this will put something into the database and it never gets removed. Be careful not to put a replicated send and a replicated receive at the same spot, otherwise they'll eat each other up until your gas runs out. You can write infinite loops. You probably don't want to. So the double bang is the permanent send. There's the example of consuming each other. Here, when we add logical connectives, this says, when I get something, and I'll call it x, and that x is not 5, that's a negation. So Kyle was talking about adding logical connectives as something he's working on, from coins, and I get another one, let's call it y. So this one, x, is not a nickel, and y is not a dime. Then, and x plus y equals 15. So this is a conditional. We're going to have conditionals in the for expressions. They're not in yet, but they're going to be. So if we get these things and this condition is satisfied, then we'll print them out. Well, the answer to the riddle is a dime and a nickel, since a dime is not 5 cents and a nickel is not 10. Right, we are out of time. That said, I'm going to take just a minute here. If you go to the GitHub repo, download that. You can find under Rholang tests, Mercury tutorial, there are a bunch of tests that are actually being run as part of the build process. I've modified a couple of them here just to make it easier to read what comes out. The project drawer. Remember that it doesn't accept new lines, so I have to remove them before I paste them in here, but I can do this, and it shows me what it parsed, what it's evaluating, and what the results were. So in this case, let me go back to this so it's easier to, look at. This says we're just sending true on Hello World. Hello World is listening with the contract, so the contract won't be removed, but every time it receives something, it'll fire out the same thing it received on test result. So if we go back over here, we see that the contract is still there, and you'll notice that it's encoded as a replicated for, because contracts and replicated for mean the same thing. It's just intent to pay that's different. And because we fired off Hello World, true, the interior of this said, well, send the same thing on test result, and so we see here that there is a message waiting on the key test result. I'll shut it down and start it up again so we don't have old data laying around. Here's an example of a function. This is squaring plus 1. So it's expecting a number to square and a return channel to send the answer back on. So it says x times x plus 1 and sends it on return. So this invokes that function with the value 5 and says send it on the name live demo. So here we get the contract still listening on square plus 1, but we sent 5 and we got live demo bang 26. So in that key, at that key of the database is stored the value we were expecting. I didn't expect to spend quite so much time on the tutorial, but you can continue and go through, do that sort of thing. It's fairly clear using the, here's the return channel, everything else is pretty much the same. You can do your functional arithmetic style stuff in Rholang pretty quickly. I encourage you all to go play with it. Just download the Docker, fire it up. Let us know how it goes. Let us know if you're running into something that's giving you trouble. We'll be happy to help you out. Thank you very much.